Right now, as you watch this video, the ground beneath your feet is moving. The tectonic plate you're standing on is shifting. Not quickly, just 2 to 10 centimeters per year, about as fast as your fingernails grow. That sounds harmless, barely noticeable. But that slow, relentless movement is responsible for every major earthquake, every volcanic eruption, and every tsunami that has ever occurred. Today, we're explaining how fast tectonic plates actually move, why they move, and why something so slow can be so catastrophically destructive. Because when tectonic plates collide, the results reshape continents and destroy cities. Tectonic plates don't all move at the same speed. Some are racing across the Earth's surface, relatively speaking, while others crawl along at barely perceptible rates. But even the fastest plates are moving slower than you walk. The Pacific Plate is the speed demon of tectonic plates. It moves at 7 to 11 centimeters per year. That makes it the fastest major plate on Earth. The North American Plate, by comparison, moves at just 2 to 3 centimeters per year. The Eurasian Plate moves at 2 to 4 centimeters per year. The Australian Plate moves at 6 to 7 centimeters per year, making it relatively fast. And the Antarctic Plate is the slowest of the major plates, moving at just 1 to 2 centimeters per year. To put this in perspective, your fingernails grow at about 3 to 4 centimeters per year, which means some tectonic plates move slower than your fingernails grow. A garden snail moves faster than tectonic plates. But over time, these tiny movements add up. In your lifetime, assuming you live 80 years, the tectonic plate you're standing on will move between 1.6 and 8 meters. That's about the length of a small car. Since the year 1900, the Pacific Plate has moved about 13.75 meters. The North American Plate has moved about 2.5 meters. That's not much in a human time frame. But go back further. Since the fall of the Roman Empire, about 2,000 years ago, the Pacific Plate has moved about 220 meters. The North American Plate has moved about 40 meters. And over millions of years, the distances become staggering. In 1 million years, the Pacific Plate moves 70 to 110 kilometers. That's enough to completely rearrange the geography of entire regions. Continents split apart. Oceans open and close. Mountain ranges rise from flat plains. Over hundreds of millions of years, tectonic plates have rearranged the Earth's surface countless times. The continents as we know them today are just a snapshot in an endless cycle of movement and change. So why do tectonic plates move at all? The answer lies deep beneath the Earth's surface, in the mantle. The Earth's interior is incredibly hot. The core, at the center of the planet, reaches temperatures of over 5,000 degrees Celsius. This immense heat creates convection currents in the mantle, the thick layer of semi-molten rock between the core and the crust. Hot material rises toward the surface, cools, and then sinks back down. It's the same process you see when you boil water in a pot. Hot water rises, cools at the surface, and sinks back down, creating a Sun Huan pattern. These convection currents in the mantle drag the tectonic plates along. The plates are part of the lithosphere, the rigid outer layer of the Earth that includes the crust and the uppermost part of the mantle. The lithosphere floats on the asthenosphere, a more ductile, partially molten layer beneath it. As the mantle convects, it moves the plate sitting on top of it. But convection isn't the only force at work. There are 2 other major mechanisms that drive plate movement: slab pull and ridge push. Slab pull is the primary driver of plate tectonics. When an oceanic plate collides with another plate at a subduction zone, the denser oceanic plate sinks into the mantle. As it descends, gravity pulls on the entire slab, dragging the rest of the plate behind it. It's like pulling a tablecloth off a table. Once you start pulling one edge, the whole cloth slides along. Slab pull is incredibly powerful. It's the main reason why the Pacific Plate moves so fast. Large portions of the Pacific Plate are subducting beneath the plates around it, and that sinking material is pulling the entire plate forward. Ridge push is a secondary force. At mid-ocean ridges, new oceanic crust is constantly being formed as magma rises from the mantle and solidifies. These ridges are elevated compared to the surrounding ocean floor. Gravity causes the newly formed crust to slide away from the ridge, pushing the plate outward. Ridge push is much weaker than slab pull, but it contributes to the overall movement of plates. The result of these forces is that tectonic plates are constantly moving in different directions. Some are spreading apart at divergent boundaries. Some are colliding at convergent boundaries, and some are sliding past each other at transform boundaries. Each type of boundary produces different geological features and hazards. At divergent boundaries, tectonic plates move apart. The most famous example is the Mid-Atlantic Ridge, where the North American Plate and the Eurasian Plate are separating. They're moving apart at about 2 to 3 centimeters per year. As the plates separate, magma rises from the mantle to fill the gap, creating new oceanic crust. This process is called seafloor spreading. The Atlantic Ocean is growing wider because of this. Meanwhile, the Pacific Ocean is shrinking because its edges are being consumed at subduction zones faster than new crust is being created. Most of the Mid-Atlantic Ridge is underwater, but there's one place where it rises above sea level: Iceland. Iceland sits directly on the ridge, and you can actually see the boundary between the North American and Eurasian plates. The island is being torn in two, very slowly, as the plates pull apart. The result is volcanic activity, geysers, and frequent earthquakes. New crust is constantly forming in Iceland, making it one of the most geologically active places on Earth. Convergent boundaries are where plates collide, and this is where the most dramatic and destructive geological processes occur. There are 3 types of convergent boundaries, depending on what types of crust are colliding. When an oceanic plate collides with a continental plate, the denser oceanic plate is forced beneath the continental plate in a process called subduction. The Pacific Plate subducting beneath the South American Plate is a perfect example. This collision has created the Andes Mountains, the longest continental mountain range on Earth. As the oceanic plate descends into the mantle, it melts, and the magma rises to form volcanoes. This is why the Andes are studded with active volcanoes. It's also why this region experiences frequent and powerful earthquakes. The 1960 Valdivia earthquake in Chile, the largest earthquake ever recorded at magnitude 9.5, was caused by this subduction zone. The subduction of oceanic plates beneath continental plates is responsible for most of the volcanoes in the Pacific Ring of Fire. The Cascade Range in the Pacific Northwest, the volcanoes of Japan, the Philippine volcanoes, and the Andes all exist because of this type of plate collision. When 2 oceanic plates collide, one subducts beneath the other. This creates deep ocean trenches, the deepest places on Earth. The Mariana Trench, which reaches a depth of nearly 11,000 meters, was formed by the subduction of the Pacific Plate beneath the Mariana Plate. These collisions also create volcanic island arcs. Japan, the Philippines, and the Aleutian Islands are all examples of island arcs formed by oceanic convergence. These regions are prone to powerful earthquakes and explosive volcanic eruptions. When 2 continental plates collide, neither subducts because continental crust is too buoyant. Instead, the crust crumples and thickens, forming massive mountain ranges. The collision between the Indian Plate and the Eurasian Plate has created the Himalayas, the tallest mountain range on Earth. This collision is still happening. India is moving north at about 5 centimeters per year, and the Himalayas are still rising by about 5 millimeters per year. This ongoing collision causes frequent earthquakes in the region, including the devastating 2015 Nepal earthquake. Transform boundaries are where plates slide past each other horizontally. The most famous example is the San Andreas Fault in California, where the Pacific Plate is sliding northwest relative to the North American Plate at about 5 centimeters per year. Transform boundaries don't create volcanoes because there's no subduction, but they do generate earthquakes. The grinding and friction between the plates creates stress that builds up over time. Eventually, the stress is released in a sudden rupture, causing an earthquake. The 1906 San Francisco earthquake, which killed over 3,000 people and destroyed much of the city, was caused by a rupture along the San Andreas Fault. So if tectonic plates move so slowly, why are the earthquakes they produce so destructive? The answer lies in the way the movement happens. Tectonic plates don't slide smoothly past each other. Their surfaces are rough and irregular, and they lock together because of friction. Even though the plates are being pushed or pulled by the forces in the mantle, they can't move because they're stuck. Stress builds up along the fault. Year after year, decade after decade, the stress accumulates. And then, suddenly, the friction is overcome. The plates snap into their new position, releasing all the built-up energy in seconds. This sudden movement is what causes an earthquake. Let's take the San Andreas Fault as an example. It moves at an average rate of 5 centimeters per year, but it doesn't move 5 centimeters every year. Instead, sections of the fault remain locked for 50 to 100 years or more. During that time, stress builds up. Then, in a matter of seconds, the fault ruptures and the plates slide 2 to 5 meters past each other. That sudden movement generates seismic waves that shake the ground violently. The longer the fault remains locked, the more stress builds up and the larger the eventual earthquake. Subduction zones are even more dangerous. At subduction zones, the plates can remain locked for 200 to 500 years. When they finally rupture, they can move 10 to 20 meters or more. This produces magnitude 8 or 9 megathrust earthquakes, the most powerful earthquakes on Earth. And because subduction zones are underwater, the sudden vertical displacement of the seafloor generates tsunamis. The 2011 Tohoku earthquake in Japan was a magnitude 9.1 megathrust earthquake. The Pacific Plate suddenly lurched beneath the North American Plate, moving up to 50 meters in some places. The vertical displacement of the seafloor created a tsunami that reached heights of 40 meters and traveled across the entire Pacific Ocean. The key point is this: it's not the speed of plate movement that's dangerous. It's the sudden release of accumulated stress. Slow, continuous movement would be harmless. But because the plates lock together and then suddenly slip, the result is catastrophic shaking and destruction. How do we know how fast tectonic plates are moving? Scientists use several methods to measure plate motion. The most accurate is GPS technology. GPS stations around the world track the positions of tectonic plates with millimeter precision. By measuring how these stations move over time, scientists can determine the speed and direction of plate movement. GPS can detect changes as small as 2 centimeters per year, which is perfect for studying plate tectonics. Geological evidence also tells us about plate movement. When Pangaea, the supercontinent, broke apart about 200 million years ago, the fragments drifted to their current positions. We know this because fossils of the same species are found on continents that are now separated by oceans. The fit of the coastlines of South America and Africa, the matching geological formations, and the distribution of ancient glacial deposits all support the theory of continental drift. The ocean floor provides even more evidence. As new crust forms at mid-ocean ridges, it records the direction of Earth's magnetic field. Every few 100,000 years, Earth's magnetic field reverses. The newly formed crust captures this magnetic signature, creating a striped pattern on the ocean floor. By measuring the width of these magnetic stripes and knowing how long ago each reversal occurred, scientists can calculate how fast the plates have been spreading. Satellites also play a role. Interferometric synthetic aperture radar, or INSAR, uses satellite imagery to measure ground deformation with incredible precision. This technology can detect changes as small as a few millimeters, making it useful for tracking plate movement and identifying areas where stress is building up along faults. What does the future hold for tectonic plate movement? The plates won't stop moving anytime soon. In fact, they'll continue to reshape the Earth's surface for billions of years. The Pacific Ocean will keep shrinking as its edges are consumed at subduction zones. The Atlantic Ocean will continue to grow as the mid-Atlantic ridge creates new crust. Australia is moving north toward Asia at about 7 centimeters per year. In 50 to 100 million years, Australia will collide with Asia, creating a new mountain range. Africa is splitting apart along the East African Rift. In tens of millions of years, the eastern part of Africa will break off, and a new ocean will form between the pieces. The Mediterranean Sea is slowly closing as Africa moves north toward Europe. Eventually, the Mediterranean will disappear, and Africa and Europe will collide, forming a new mountain range. In about 250 million years, scientists predict that the continents will come together again to form a new supercontinent. Some call it Pangaea Proxima or Pangaea Ultima. The exact configuration is uncertain, but the process is inevitable. continents drift apart, and then they come back together. It's a cycle that has repeated multiple times throughout Earth's history. But long before these far future events occur, we'll experience many more earthquakes and volcanic eruptions caused by plate tectonics. The Cascadia subduction zone off the coast of the Pacific Northwest is locked in building stress. When it ruptures, it will produce a magnitude 8 or 9 earthquake and a tsunami that will devastate cities like Seattle and Portland. The San Andreas Fault in California will eventually produce the big one, a massive earthquake that will cause widespread destruction. The Manila Trench off the coast of the Philippines is capable of a magnitude 9 earthquake that would threaten millions of people in Metro Manila. These events are not a matter of if, but when. Tectonic plates move slowly, just a few centimeters per year. But over millions of years, they reshape continents, build mountains, and create oceans. And when that slow movement suddenly releases, it destroys cities, triggers tsunamis, and changes landscapes. The ground beneath your feet is moving right now. It has been moving for billions of years, and it will keep moving long after we're gone. Understanding how tectonic plates move and what happens when they collide is essential for predicting earthquakes, preparing for disasters, and comprehending the dynamic planet we live on. If you want to learn more about plate tectonics, earthquake threats, volcanic activity, and the forces shaping our planet, subscribe to this channel. We break down the science behind natural disasters and help you understand the Earth beneath your feet. Because beneath the depths, the planet never stops moving.